Welcome back, and now we are looking at significant figures. So, the general rule, we'll just read through this to start off with. The general rule is that the more figures used to express a quantitative result, the more precise the reading. Scientists often refer to this measure of precision by reference to the number of significant figures. So, consider the following data. We have measured a mass of an object as 16 grams, and it has two significant figures. 15.8 grams for another object with three significant figures. This one here, 15.78 with four significant figures. And the mass of the object, 15.782, is five significant figures. So, as you can probably see, all these ones, all the masses here, are very similar. They're all around about 16 grams. But depending on the measurement device and also the degree of precision that you need, you'll want to go to more or less decimal places. So if you're, say, baking a cake, then the mass of the object, 16 grams, is two significant figures is probably fine for that, for making a cake. But if you're, say, launching something into space, you need something like five significant figures or possibly way more than five significant figures, depending on how precise the data is. So, the more accuracy just depends on basically the consequence of having more or less accuracy or precision. So the number of significant figures in the example above is quite easily established, but numbers with zeros at either end, such as 120, or at the beginning, and 0.012 can be presented a lemma. So obviously these ones are pretty easy because there's just two numbers here, three numbers here, four numbers for this one, five numbers for that one. So that was pretty easy. But these ones here, when we have zeros, it can become a bit more confusing. So the first rule here, is zeros used to locate the decimal point are not significant. So these zeros in front of the decimal place, they're not significant, but these last three are. So they're three significant figures. Similarly, the second one has two significant figures, even though there's five numbers in total in both of those. Okay, so the second rule here, zeros used before the decimal place may or may not be significant. So this is where the confusion comes in, because 140 kilos, if you look here, if it's to two significant figures, if we just count the 1 and the 4 as significant, then the mass can be anywhere between 130 and 150 kilograms. So there's quite a large difference between 130 and 150 kilograms. But if it's the nearest kilogram, so if this zero is significant, so three significant figures, then it's only between 139 and 141 kilograms. So we know much more precisely how much this object weighs. Okay, so to avoid confusion, there is scientific notation down here. Okay, so like we said before, the mass of an object, if it's 140 kilograms, then it can be two or three significant figures. But if we represent it here, so scientific notation is one number with decimal places after it, and then it's times by 10 to the power of its order of magnitude. Okay, so 1.4, if it's two significant figures, then it'd be 1.4 times 10 to the 2, and then our object would be this one here, so it'd be 130 and 150. But if we write it like this, with 1.40, this number here is significant also, and so we know that our object is between 139 and 141 kilograms. So that's really the power of scientific notation. And I just want to go through some of these problems for you and leave some for you to do yourself. So we'll just go with question 2a. So if we have 1300 to two significant figures, all we do is we say 1, so we always put our first number first and then put a decimal place there, to two significant figures, so we just include the 3. But because there's 1, 2, 3 zeros after our 1, we put that as times 10 to the 3. Okay. Now, to three significant figures, this time we include 1 point, so we still put the decimal place after our 1, but this time it's 1.30, but our order of magnitude is the same still. It's still the same number, so it's times 10 to the 3 again. Oops. Okay. Now, C and D are quite similar, so I'll let you do those ones, and there are answers at the bottom of this page as well. So we'll skip ahead to question E now. And so we're going to 3 significant figures this time. And what we need to do is put our decimal after the first number. So we can see here our first number is 4. So it's going to be 4.74 because we've got 3 significant figures. So we include our 7 and 4 in there. And then because there's 1, 2, 3 numbers before or after the decimal, and before our first significant figure, this is equal to 10 to the negative 3. Okay, and that's why we wanted to start off with our powers of 10 earlier. So if you're not sure about that, maybe go and have a look over that powers of 10 stuff again. Okay, so we'll go to G, and 1 million. So 1 million. So million is, the order of magnitude is 10 to the 6. So it's 1 with 6 zeros after it. So 1 million to 2 significant figures will be 1.0 times 10 to the 6. Okay. 4 significant figures here for this one. It is, we put our 1 down there, and then we've got 3 zeros after it, so it's 1.789. We want to include all of those times 10 to 3. And so far we haven't had to do any kind of rounding because everything's just been nice for us. That's why I wanted to include these last 3 on the end. You do need to be able to do rounding. So I'm just going to do J. So 45.8 times 10 to the 3. Okay, so what we need to do is put the 4 down. And then the significant figure, we're only going to include 1 significant figure. And see how the number after the 5 is larger than 5. So we have to round up to 6. So just remember your rounding rules. Yep, rounding. If it's 1, if the number after is 1 to 4, then no rounding. But if it's like 5 to 9, round up. And round up just means we increase the number that we're looking at. And because this is 45.8, see how we've had to shift the decimal place back this way, we actually have to increase our order of magnitude. Okay, so if we were to write this out in full, it would be, we have 45.8 times 10 to the 3, so that is actually equal to 45,800. Okay, so sometimes it is useful to write those out. So if we then had to change that to 2 significant figures, it might be easier for you to say, well, there's 4.6 times 10 to the 4 because we've got 4 there, 1, 2, 3, 4. Yeah, so don't be afraid to write out the numbers in full if that makes it easier for you to find the scientific notation if it's a case like this. Okay, I'll let you do the rest of those problems.